Physics Lecture 5, Fluids. Before we start, let's talk about what a fluid is. A fluid flows and conforms to the shape of its container. This is quite the contrary to a solid, which retains shape and has no flow. Note that fluids can be gases or liquids. Density is a scalar quantity. Put simply, it is mass over volume. Every compound has its own specific density. This can be used to identify elements. Two other specific characteristics of fluids are weight and specific gravity. One is represented by force equals density times volume times gravity. This is the weight of a substance with a known density. Specific gravity is a comparison between the density of a fluid versus that of pure water. Water has a density of 1 gram per centimeter cubed. Specific gravity is commonly used to test urine. A specific gravity that is abnormal usually indicates a physiological problem. Pressure, put simply, is the ratio of force per unit area, and the SI unit for which is pascals. This is also a scalar quantity. You need to understand how pressure is related mathematically. It is force over area. Think about how a change in force or area would affect pressure. A larger force would increase the pressure, whereas a larger area would decrease it. There are three types of pressure that we will discuss during the lecture. The first is atmospheric pressure, or the pressure of your surrounding atmosphere. This changes with altitude. Depending on whether you're at sea level or at higher elevations, this will affect your atmospheric pressure. So make sure you take note of that if you're looking at passages and trying to figure out which value to use for your atmospheric pressure. Let's put this into an example here. If we were to talk about Denver, which is 5,280 feet above sea level, they have an atmospheric pressure that is slightly less than sea level. Their pressure is noted at about 632 millimeters of mercury, or 0.83 atmospheres. If you were to go to sea level, it would sit more around 760 millimeters of mercury, or 1 atmosphere. As you can see, the higher the elevation, the lower the atmospheric pressure. The next pressure we'll go into is the absolute pressure. This is also known as hydrostatic pressure. This is the total pressure exerted on an object that is submerged in a fluid, the equation of which is listed below. Please note that P0 is not necessarily always going to be atmospheric pressure, so be careful with that come test day. Gauge pressure is a measure of the difference between absolute pressure and atmospheric pressure, the equation for which is listed below. Simply put, it is P minus the atmospheric pressure. So you're taking the absolute pressure and subtracting atmospheric pressure from it. This will net you your gauge pressure. Now that we've covered some characteristics and fundamentals of fluids, let's talk about hydrostatics. The first principle we need to go into is Pascal's principle, which states that for incompressible fluids, force will be evenly distributed throughout. The piston is a very common example that is used on come test day. If we were to draw a piston, something like so, with a area 1 and a area 2. As I compress this down with a force, we'll call this force 1. The resulting force F2 from this compression, as this force is applied, has to equate such that the two expressions are equivalent to each other. Note, this is going to result in some sort of displacement. So I will call this D1, and I will call this D2. With respect to displacement, we have the expression listed here. If you were to combine the two, you would get something that looks like this, stating that the work is equivalent to pressure times the change in volume. Note, this is how hydraulic jacks work. You take a smaller area and apply a force. That force is evenly distributed through the incompressible fluid, allowing for you to lift heavier objects. Archimedes' principle. Many of you have probably heard the tale of Archimedes and the crown. The king was offered a crown by a jeweler, who swore that the crown was pure. However, the king had his doubts, so he asked Archimedes to figure out a way to determine whether or not the jeweler was being honest with him. Archimedes scoured and pored and thought about this for quite some time. How could he figure out the composition of the crown without destroying it? Finally, he decided to take a bath, and when he sat in the water, he immediately stood up and said, "Eureka, I have it." This is commonly held to be where the term eureka came from. But I digress. Archimedes figured a way to find out whether or not the crown was pure. Archimedes pioneered the concept of buoyant force. Simply put, it states that the volume of the fluid displaced has to equal the volume of the submerged object. So, if the crown was indeed pure, it should displace the same amount of fluid as the same equivalent weight of pure compound. Now, I would tell you how this story ends, but I think I'll leave that up for your own discovery. Just note that on the MCAT, you will have to use this equation for calculations. Let's talk about some molecular forces in liquids. For starters, let's talk about surface tension, which is the surface layer on top of the liquid. Think of this as a film or a skin that's on top of the liquid. It's a result of cohesion between the molecules of a fluid. This would explain why water striders can slide along water. They're abusing the surface tension of the water along with their own physiology to skirt above the surface. Adhesion, on the contrary, is the attractive force felt between molecules of the fluid and another substance. Make sure you have a clear understanding of the difference between cohesion and adhesion. This plays into the meniscus. For a normal meniscus, it looks something like this. So if we had a container and the liquid were to bow down, like so, we can state that the adhesive force is greater than the cohesive force, or that the liquid is more inclined to stick to the other substance, or the container walls, than it is itself. This is the more common form, but a backwards meniscus is also possible. For a backwards meniscus, as the name suggests, the semicircle, or the shape of the fluid in the container, goes the opposite direction, like so. This states that the cohesive force is greater than the adhesive force. So the liquid is more inclined to stick to itself than it is the container. Now that we've talked about hydrostatics, let's talk about fluid dynamics, or how fluids move. First and foremost, fluids do move, but they do resist flow and movement. This is called viscosity. Viscosity is somewhat analogous to air resistance, except for liquids. Depending on the viscosity of the liquid, it will have a specific kind of flow. An example of this would be the difference between water and something that's incredibly viscous, for example, maple syrup. If you were to pour these two simultaneously, you'll notice that one flows at a faster rate than the other. Laminar and turbulent flow. At the top, we have what's listed as turbulent flow, right here. At the bottom is something called laminar flow. As you can see, one is a little bit more even than the other. Poiseuille's law, which is listed here, and critical speed are going to be calculations you will have to run on the fluids for these two types of flows. As you can see, Poiseuille's law is very complicated, but it boils down to something a little bit more simple. It simply states that the flow rate is equivalent to the change in pressure over resistance. What you'll notice when we go into electricity and magnetism is that there are certain factors that play into resistance for a current. You'll notice that these also apply for fluids and liquids. It's very similar. So if you know what affects resistance, and you know what's going to affect pressure, you can generally solve problems for these sorts of flows without doing the full-on calculation. Again, it's more important for the MCAT to have a conceptual understanding rather than to just memorize everything. Streamlines are arrows that indicate pathways followed by tiny fluid elements as they move. If you remember from our first unit, they're very similar to free body diagrams and the vectors that you will draw. Think of it in that sense. It's a representation of the fluids as they move. For the MCAT, this will play into linear speed, which is stated below. It states that the velocity at a given area has to equal the velocity at all other areas of the system. As you can guess, as the area gets smaller, the velocity will have to increase. So if I were to have values listed, if I have a larger area and a velocity, as the area gets smaller, the velocity has to increase to keep this equivalent. By far, the most important equation in this entire section is Bernoulli's equation. If there's one equation you need to commit to memory, it is this one. This one will be tested, and your understanding of this equation and the principles that apply within it will be challenged. It's a sort of an extension of the linear speed, but it combines a lot of different pressure elements that we've already discussed earlier in this lecture. It's comprised of two terms. The first is 1/2 density v squared, which refers to the dynamic pressure, or the pressure associated with movement. I'm sure you've noticed this, but that equation looks an awful lot like the equation for kinetic energy, and you'd be right. That's generally a good way to keep the two separate and to make sure you understand which one is associated with the movement. P versus rho gh, on the other hand, is referring to the static pressure. Think of this as sort of potential, or the pressure that it has sitting still, or static. For a given system, it has to equate at every point along the path of the fluid. The most common way that the Bernoulli's equation is going to be tested on the MCAT is the Venturi flow meter, a system for which is listed below. What you'll be asked is, at each point in the pipe or in the system, what height is the liquid going to be at and why? If we remember what the Bernoulli's equation looks like, and I will just write out one little bit of it here. P1 plus 1/2 rho V1 squared plus rho GH1. This has to equal P2 plus 1/2 rho V2 squared plus rho GH2. Let's treat this area as area 2 and this area as area 1. Which would you expect to have a higher height? Well, it would be this one. And why, do you ask? As this gets smaller around area 2, right around here, there's a smaller area, which means that the velocity increases. An increase in the velocity will cause this term to increase as well. But if that's the case, we need to make sure these still are equivalent, don't we? So, where is it going to give? Well, it's going to be in the height. So, at this area, area 2, the height experienced by the liquid is going to be lower. That's how we keep these two equivalent. Make sure you understand how this system applies and how you can use the Bernoulli's equation to figure out where things will be and conceptually what's going to happen at each site. So that'll do it for our discussion of fluids. Please join us in the next lecture as we go into electrostatics and magnetism.